And I guess this is for the Zoom audience,
Yes.
right?
Yes.
You got it? Does it sound okay? Okay, good. Well, first, I want to thank Professor McQueen and Professor Kushwaha for the opportunity to be with you all today. I must say, this is the first time I have stepped inside a building at Johns Hopkins. When my daughter was looking for undergraduate schools, we came and we said, okay, I can't afford this place. Can you go on somewhere else? So you don't know how lucky you are, I think, to be inside Johns Hopkins. So the one thing that you will, as he said, as Tyrell said, Dr. Bhatia and I are collaborating on this talk, right? I mean, and so we want to talk about quantum technologies and then intersperse that with a conversation about how to do collaborative technology development and exhibit collaborative leadership. Um, so just, I decided to wear my NY Creates t-shirt here. NY Creates is the best kept secret in New York State. So we are home to the most advanced publicly owned semiconductor fabrication facility in the United States. And, all the technologies that you might see in announcements by IBM on 2 nanometer node CMOS, all of that happened at this facility. Uh, and there is a whole bunch of space here. Unfortunately, this was taken in winter, so there are no green trees. But believe me, the campus is a lot more beautiful than this picture leads you to believe. There are all of these buildings are full of clean room fabs, and I like to joke that if you have a car parked in a parking lot, the next day the parking lot will disappear. There'll be a new building that is coming up. In fact, this space is going to house the next nanofab clean room. It's called nanofab reflection because it reflects off of this building. Is the same size. So there's nanofab extension, nanofab center, nanofab south, nanofab north, nanofab east. The only thing that is not nano is there is a nano cafe, but the prices are not nano there. So um, because of the equipment investment that is present in these buildings, right? The buildings themselves cost half a billion dollars, right? But the equipment that is there over the past 3 decades represents a cumulative 15 billion. We have the fortune of working with all the leading manufacturers. They have their home here. I will talk about the collaboration that we have with them. The advantage is that they bring their best and latest tools there, and we're able to leverage those for our purposes as well. The going on, any tool that you see, I was talking to Raja, he said, he works with Intel. If you go to Intel, you go to Global Foundries, you see 300 millimeter fabrication tools. You will see the same tools at our fab. Here is a ASML lithography tool. You will see all these, most of the time, we do not use overhead transport like this. In most of the real fabs, all the wafers are transported on that. The wafer goes, the FOUP, as it's called, knows where it is going, thanks to a manufacturing execution system. Once it lands there, the recipe is downloaded from the cloud and executed, and so on and so forth. The only reason why we have it only between two buildings and not inside the building is because we are constantly changing our tools as we upgrade, right? And I want to say, there are other people like the Senate Majority Leader currently, the Governor of New York that have come visited. So you should come visit too. I want to say I'm happy to give you a tour. I love, showing off. Ekta and I have done this many times. Any tool that you see here will be part of what you see in a manufacturing facility, and that is one of the strengths that we bring to place. So the question that I face whenever I put in applications for funding from it, so why 300 millimeter scale? Is particularly quantum. Is quantum ready for 300 millimeter wafers? Are we going to ask for so many qubits when we don't even know how to make 5 qubits work together, right? But the answer is it is not about the wafer size or the number of chips that you can get out. The answer is that the tools that are there in this fab represent the fruits of hard labor by the semiconductor industry over the past, would you say, 60 years, right? And so every technology advancement that has been incorporated, they tend to put it into 300 millimeter scale. And I actually asked a fab vendor, I said, okay, clearly I feel greedy about this new technology, but you are company XYZ, you can easily backfill that technology and put it into a 200 millimeter tool. And the answer is no, because the market demand has got to exist for them to do all of that work back again to put it into older technology. So the reason we are working on 300 millimeter scale is because we have the advantage of the exquisite interface control, the cleanest materials that can be put down in semiconductor wafers, silicon wafers. That is the one big constraint that we have. It has to be on a 300 millimeter wafer. And so a lot of the quantum work right now is done on sapphire, small diameter wafers. We cannot do that, but there are other advantages. What are some of the other advantages? Fab infrastructure, right? So I should explain what I mean by signal to noise ratio. Right. When you run an experiment, you have a signal, you've got a noise, and you want to make sure the signal to noise ratio is high. In the context of fab infrastructure, what I'm trying to say is that if you run experiments, the signal that you're looking for is, did this experiment work? Did material X perform better than material Y? And if you're going to have to suffer from noise, because it's not just a single experiment that you're doing, it is going through multiple steps, and you need to know whether or not a null result is the result of, or worse, a false negative is because of noise that was introduced in the experimental process, or because it was really so. When you have process control, and my colleague Dr. Bhatia will talk in great detail about that, you are able to make sure that your experiments conclusions, you don't need to repeat so many times, right? We still do experiments a couple of times. It's not like one and done, but we want to make sure that we can rely on the results. One thing, and this is more of a it's a pity that it's being recorded because I'm sure it's going to come back to bite me. But materials, I think, in the quantum have been blamed when in some cases it is a fabrication process that is not optimized for this material, right? I mean, there was a long time when people said, okay, aluminum bad. But then last few months ago, Ekta and I listened to a presentation at APS and said aluminum has got very high coherence time. So it is not the material itself that is the issue. And not surprisingly, it's the interface that it forms, the damage that might be created in the substrate. All of these have the benefit of being better when you use advanced tools. The other major thing that we do is, we have to make reproducible technologies. We are driven by that. We are consumed by that, right? It doesn't make sense. And I've been in places, I've talked to faculty, and I've talked to my colleagues at some of the other places that I've worked at before, because I don't need to do that again. If I get that science paper, that is enough. I don't need to worry about it. But that's not the way we operate, right? That particular story is true, by the way, right? I said, oh, this will not work the second time because we are handcrafting it. It was okay, so long as he got the proof that it is feasible, right? But for us, the name of the game is to develop reproducible technologies so that they can come again and again. Now, what is our relationship to academic labs such as yours, right? Or collaboration facilities like Paradigm? They are essential because we cannot move as fast as you guys can move. We don't have e-beam lithography. We cannot introduce a new material into the fab the minute you think it is possible, right? We have to go through a change review board, and there'll be 10,000 people asking you questions, why you need this, or how you will return the tool back to a steady state. In the sense that, like I said, IBM is making the 2 nanometer technology development there, right? 2 nanometer CMOS node. Imagine if they walk up to the tool, or so to speak, walk up to the tool, and their next lot of wafers is ruined because I ran an experiment in there and I left it contaminated. So we have very strict protocols that the tools get qualified. And again, I think Bhatia will talk more about it. We make sure that the tool state is well known, right? Metallic contamination, particle contamination, we take lots of effort in order to do that. So, which slows us down, right? And so we wait for the advancements to come from smart people like you and then we work to, to adapt that into 300mm scale. So some of the examples that I wanted to give you, and again, let me say, it is far easier if you come visit so that you can see for yourself what these things are like. CMP tools. CMP is chemical mechanical planarization, right? And so you use that process repeatedly in IC fabrication in order to build a multi-layer stack or even the transistor level as well. In the days gone by, you would run a CMP process and you would actually run what's called a send-ahead wafer. You would say, okay, did that work? Okay, now I can commit the rest of the wafers through the tool. And Applied Materials came up with this process. Here, it shows an eddy current sensor which senses the thickness of the metal across the wafer diameter, right, or across the wafer surface. And it is constantly recording it. That data is being fed back. And here, I cannot click on it. It's a picture, but the pressure in about 6 zones is adjusted dynamically in order to make sure that at the end, the thickness is ending up flat across, flat or zero, if it's a metal that you want to remove, across the entire wafer surface. Back when I was at TI and we didn't have this, we would continuously tune the process, right? Whereas here, any variability in the tool is taken care of by the automation, by the in situ capabilities of the tool to sense. So this talks about metal CMP. And then let's say you want to have a dielectric material and you want to remove that and planarize it, right? And by the way, does planarization make sense to you? Why would you want to planarize it? Why would you want to planarize anything? That is one possible reason. The bigger reason is in the way back when, before you were born, people were using eye-line lithography, right? That had large depth of focus, right? You could print on the wafer surface, and it didn't matter that the wafer surface had hills and valleys. If you got a metal line and you deposited dielectric, it went over that, and it was about a micron of height difference. And yes, eye-line lithography could handle that. You could print lines nicely. Whereas in modern lithography tools, the depth of focus is so small that you cannot afford to have that. So that is one major reason why planarization came into effect. There are other reasons, of course. Contamination is useful, but because of the planarization, you need to be able to planarize both metals as well as dielectrics. And how do you know that you have polished away a certain thickness of dielectric and you want to stop when across the wafer you have 30 nanometers of dielectric? You couldn't have. In fact, that was my job when I was at TI. And you had to run, again, send ahead wafers, measure it, and then run back to the tool before somebody complained, and then finish running the rest of the wafers. Whereas here, this is basically, in this day age of AI, this picture is before AI became all hot, right? So it measures the reflectance of the wafer at various wavelengths, bright light, and then it develops a model that says when the signal looks like this, a certain thickness that you as the engineer or as the scientist have determined. So, here is the rate at which the polish is happening, and okay, lo and behold, it is done at a certain time, and you're done. So all of these are technologies that are available in the latest tools. And already, Ekta and I were talking to our colleague, and she was telling us there is something even better than this that AMAT is working on. And that is one of the advantages of working at NY Creates, because all of these new tools are coming in, and we can take advantage of them. Reactive ion etch, RIE stands for reactive ion etch, right? And so currently, when you etch a wafer, maybe you say, okay, the center is good, or the edge has gone bad, or vice versa. Whereas in state-of-the-art tools, you are able to control the temperature of the focus ring, so there's to adjust the rate. You can change the gas input. You can change the ratio. You can change the ratio in situ while the process recipe is going on, and you don't need to worry about doing that because you've set it up beforehand. Here is an example of from Lam Research that shows how the temperature of the chuck, which controls the rate at which the reaction, the RIE process is happening, can be controlled in a variety of ways. And here it's almost pixelated, right? Imagine that degree of control. And you can arrange these pixels. If you say, oh, in a particular technology, I want the edge to be fast. Another one, I want the edge to be slow. You can start tuning that recipe into your rye chamber. And we use what's called endpoint detection very often, because it also allows us to get rid of the fluctuations that all tools experience, right? If you've got a rye tool, the rye rate might be different. What is this endpoint detection system? We monitor the emission that is coming from the plasma in the reactive ionic chamber. And you take various channels and you pick the channel, correlate that to an endpoint condition in the rye process. Here, we're etching off oxide and we are exposing a silicon carbonitride layer, and lo and behold, you have to run some experiments to make sure you establish that correlation. And we're able to say, yes, here is where we are exposing the silicon carbide layer. And once that is done, the signal decays once again, your rye is complete, right? And so you're able to engineer the individual steps in the processes so that you're not over etching or under etching and running into problems as a result of that. Ekta, you're going to give me the time clock, right? So that I don't steal your time. All right, so what is our strategy in terms of quantum? We want to exploit knowledge from the IC industry, right? I mean, like I said, there are 60 years of technology. And again, Ekta will elaborate on some of the specific examples. But it doesn't mean that what is there in the IC industry is immediately applicable to us, right? The thicknesses are different. The care-abouts are different. I mean, half the time we are talking to our colleagues who have decades of experience in the CMOS industry. And they say, well, why do you care about this? To take your example, contamination, it doesn't matter. It is below 1/8 to the 10. But for quantum, these, even those small contamination levels are critical in terms of the two-level systems, right? And so we are forever educating our colleagues and bringing them up to say, what works in the CMOS industry doesn't work for us. We need to adapt, modify it, and so on. The other thing that we do is, or rather, the other mindset that we want to adopt is the levels of abstraction. Now, we all know that there is a huge fabless industry, right? I mean, and of course, we're living in the era. You guys are lucky that all this $50 billion of CHIPS Act money is coming down, right? I couldn't have believed 10 years ago that there was all of this money that was going to come back to revitalize semiconductor industry in the United States. But when you think back to the 80s, what happened at that time was Maurice Chang, who used to be at TI, then went off to start TSMC. He said, the designer doesn't need to know the details, right? The designer can rely on a model, a mathematical model that allows him or her to design it, right? So we want to adopt that mindset for quantum as well. And the other thing that we do, we're a very small team, is to exploit synergies in adjacent technologies, and I'll talk about that. So to give you greater detail on the level of abstraction, obviously, if you're a data center person, you don't know any of these. You don't need to know any of the details, right? If you are Intel's chip designer, maybe you know a little bit of the details of a transistor, but you don't need to worry about it, because so long as you're able to say, here is a cache and I'm able to get the data rate to work out, because nobody has the time to know all of these. And that is another point that I think my colleague will make, is human knowledge is now more than what one brain can contain. So it is important to collaborate. So what I'm a material scientist by training, right? So for me, my ambitions extend from going from fabrication to making a simple SPICE model. That is enough, right? Somebody else can take over from there and take the SPICE model, make it into a circuit implementation, and so on. So, but in order to do this, in order for the SPICE model, and SPICE, by the way, is a software modeling system, basically a mathematical model of a device. So for that to be meaningful, your fabrication has got to be controlled, right? You cannot have one device behaving one day in summer and then behaving differently in the winter or from day to day, which is why you need to have the process control that 300 mm wafer fab can give you, the discipline that it gives you, right? Again, Ekta will talk about the discipline that we enforce. So we want to make sure that these things behave predictably so that we can represent them in a model, so that a quantum designer can say, if I put a transmon here and I put a CPW here, I know its center frequency is going to be exactly that within 50 megahertz. That's a challenge. We're getting there. We're not there yet. And that its coherence time is going to be A, and it's going to behave in that way, right? So that's what we are after. I think I'm doing well. Okay, yes. So what I want to explain what I mean by exploiting synergies, right? So imagine you start at this end where you got all these materials. And there is one important characteristic in all these materials. These are all well known to the semiconductor industry. And what is interesting, I'm sure you've seen these PowerPoint presentations somewhere where they show what were the materials of the elements of the periodic table that were used in the 1960s, that were used in the 1980s and 1990s. Except all the radioactive elements, I mean, a lot of the periodic table is now covered, right? And so, like, for instance, Kofi, when MRAM came along, those materials entered the fab. Magnesium oxide wouldn't have been in the fab in the 1990s, but because of MRAM, it is there in the fab. Aluminum nitride is in the fab. This is not an exact material, but think of all of these. Tantalum, well known in the quantum world now, but it is there in every one of your pockets. So wherever you keep your cell phones, right? The tantalum metal that is present is used by the CMOS industry as a diffusion barrier for the copper interconnect, to make sure that the copper doesn't go walkabout through the dielectric. But we, as Ekta will explain, are using it for different purposes. And so imagine you have all these materials, and then you could use them in a variety of individual devices. You could make them into high quality factor capacitors. You make them into superconducting qubits. You could make superconducting interconnect. You could use these materials to make SNSPDs. You could also use it to make high kinetic. SNSPDs are superconducting nanowire single photon detectors, right? Again, Ekta will talk more about that. So, and here are the materials that can be used for cryogenic MRAM, but actually there are some versions of these could also be used for pi junctions, right? And so there are ways in which you can utilize these materials to make various devices, but we don't want to stop there. We want to take the next step forward to say, how can we provide the levels of abstraction that I described to you, the PDK, the process design kit, that allows a designer to say, okay, we can make superconducting digital logic. And I had promised Professor Kushwaha that we would talk about superconducting digital logic, and I had hoped that by this time our contracts would be done and we would be actually doing it, but we're still waiting for the contract to be sent, to be written. But what we are hoping to do in partnership with IMEC, a consortium based in Belgium, and Cornell University and Jefferson Lab and so on, is building superconducting digital logic, not as 100 gigahertz yet, but superconducting digital logic, SFQ logic, is blazingly fast. And so when it comes to SFQ, I see maybe having a place in 6G base stations or 5G base stations, because it is able to do that. Right now, it is used exclusively by the, well, I should say exclusively, sorry, I do not know, but it is used heavily by the Navy, right? So they use that for direct software-defined radio, direct high-speed A to D conversion, and so on, because it is very fast. It is also energy efficient, right? I mean, and so one of the other projects that we were working on, where I hope we can get funding again to restart, is superconducting optoelectronic neuromorphic computing. Now, that handful of words, what does it mean? The superconducting means no dissipation, no resistance, right? So that energy loss mechanism has been turned off. We use Josephson junctions, so it uses very small pulses, SFQ pulses, that are like, attojoules of power per pulse. And optoelectronics, because all of the semiconductor electronic implementations of neuromorphic computing rely on the transistor, can only talk to a small number of transistors downstream. It's called fan out. If you've got one transistor, how many transistors can it talk to? How much current can this one transistor deliver that can go and turn on the gates for all the others, right? Fan out is impossible. You're limited by the RC, you're limited by the drive current. Whereas if you're able to use photonics, optical interconnects, right? And by the way, I should say this is inspired by design from NIST. Jeff Shainline at NIST, he's written a lot of papers on this, and we've been working closely with them. So imagine you have, and that's where this W center comes in. Imagine you have a bunch of 10,000 photons that you emit into a waveguide. You can create these microring resonators that, or couplers at a different spacing, so you can pull off 10 photons at a time. And so one emitter of 10,000 photons can distribute to hundreds of downstream neurons. Now, this is my personal perspective. I think what distinguishes the human brain from all electronic implementations is the degree of connectivity that the human brain has. Each neuron in our brains is connected to 1,000 downstream neurons. And each of those synapses, which is where they connect, are capable of learning, weights and all of that, which is what we're understanding. But superconducting optoelectronic neuromorphic computing is capable of operating at high speed, energy efficient for all the reasons that I mentioned, with the fan out, right? And so it can be 30,000 times faster than the human brain. And when I said that once at the then head of AFRO was in the audience, and he said, "Oh, Pops, I spoke to my wife. You're wrong. It is 10,000 times faster than the male brain." But we need to figure out how much faster than the female brain it is. So, so this is an example of the synergy. When we're able to make Josephson junctions, we're able to use them in superconducting neuromorphic computing. Obviously, they're not the same kind, right? The critical current density for a qubit is far lower than what you would use in superconducting digital logic, by like 2 orders of magnitude. And here the implementation is different. It needs to be connected differently. These two don't have any problem with TLSs, right? Whereas clearly here you need to worry about all the dielectrics that are present around the system. When we use aluminum nitride, we can use it also in superconducting neuromorphic computing. We hope, we put in a proposal which never went anywhere with DARPA, but we hope we can create a chip that allows us to talk to the trapped ion, by using these electro-optic effect of the aluminum nitride. So when it comes to quantum, and this is the last slide that I have, what I want to say is we want to make it easy for people to use us, right? We want to be able to work with the designers out there, the people slaving away on inventing new quantum algorithms or new quantum architectures, to say, okay, place a transmon there. I don't need to worry about whether or not my vacuum pump is up or vacuum pump is down, because we have an army of people taking care of vacuum pumps, right? So we want to design processes for reproducibility and performance. Obviously, you could have reproducible crap, and it's not very useful. We want to leverage the process control to, and this is the point I made earlier, it needs to be faithful to the designer intent, right? I mean, so when the designer says he or she wants this, the process needs to deliver that. Clearly, we have to do a lot of work, right? I mean, Professor Terrell McQueen was saying that some of your EEs, you think of a circuit design, you are leveraging a lot of the models that have been developed already when you do the circuit design. Whereas when it comes to the superconducting quantum PDK, it is new. We need to take and adapt analog technologies and RF and make sure that our designs are good. Because in the electronic world, and this transistor is here, and if there's another transistor there, if there is no electrical connection, they don't talk to each other. Whereas in a quantum chip, you could have a resonator that is here and operating at a certain frequency, and another resonator there that is close enough. These two can be coupled to each other because the microwave photon can allow them to couple. So, but we want to say the superconducting quantum PDK can be the rising tide. And what do I mean by that? If you think back to what happened when Morris Chang came up with this idea of a foundry, his foundry offered a PDK. He was not alone, but clearly he was the proponent of that. Designers from around the world were able to utilize that. And that is what made the electronics industry explode. Till that time, you needed to be a designer inside the confines of Intel. You needed to be a designer inside TI. TI, by the way, was central in developing the concept of PDK. No surprise, right? Morris Chang. But the idea is that if you're able to provide that design framework, I hope that the superconducting industry will similarly find an explosion in market value, from what it was before PDK came along with the semiconductor industry to now. So I think, thank you.
Hi, everyone. First, thank you, Pops. Thank you, Professor Queen and Professor Kushwaha. So Pops has talked about what is NY Creates and what is our motive. So I will go in detail in what we are doing at NY Creates. So before diving deep into what we are doing in terms of Josephson junctions, superconducting qubits, let's look at the trend of qubit lifetimes over past 20 years. So qubit lifetime is basically the time for which it can maintain its quantum state, and after that it relaxes into its ground state. So as you can see, there's a steady growth. Initially, in the first 10 years, the growth is mainly due to the design improvements, and then there is improvements in different aspects like design, materials, fabrication, and here now we can see that the curve is basically flattening out. So we need to work on all fronts, whether it is materials or it is fabrication, interfaces, design, everything. And what we are doing at NY Creates is improving the fabrication processes, using new fabrication processes, using new materials. Like Pope said, you have tantalum in your pockets. So we are using tantalum-based integration, and which is well known in semiconductor industry. And the good news is that tantalum is shown to be a good candidate material for superconducting qubits with better coherence times, as shown by Princeton group in 2021 and one group in China in 2022. So here, this is a 5-qubit, early 5-qubit chip from IBM. So this is a 5-qubit processor from IBM. So first I will describe what is qubit. So qubit basically consists of a capacitor and a Josephson junction, which acts as a nonlinear inductor. And this gives rise to the n-harmonic oscillator. And these two levels act as the two levels of the superconducting qubit. So in this chip, you can see this is the qubit, and these are the resonators which are used to do the readout, to read the state of the qubit, whether in which state it is. So, and these use the Josephson junctions, Josephson junctions is basically two superconducting electrodes separated by a thin tunnel barrier across which the Cooper pairs can tunnel and give rise to the superconducting current. And this is used as part of this qubit. So in these 5-qubit chips and in all the traditional chips, the junction is basically made of aluminum oxide, which is fabricated using the shadow evaporation technique, which are not scalable at 300 millimeter scale. So the point of using our fab is to develop scalable qubit devices using the state-of-the-art tools which leverage the decades of learning from semiconductor industry. So like I showed the Josephson junctions in the earlier page. So at NY Creates, we are making the tantalum-based Josephson junctions, which have several advantages. I will show all of them as I go through the slides. So here I will describe how we do the fabrication, what is our process flow, starting from the bottom electrode to the full fabrication of the junction. So as you saw on the previous slide, we need bottom electrode, top electrode, and a tunnel barrier. So first we need to establish our bottom electrode. So here we create a dielectric stack. And in this dielectric stack, we create, this is silicon nitride, silicon dioxide, and then we create a trench in this. And then we create a trench in silicon using the wet etch processes. Here, this is known as the Damascene approach, which is again an example. This is well known in semiconductor industry, but it is not used in quantum. But the advantage of using, it has several advantages in terms of the better interfaces, no silicon damage, which is important for quantum applications for the qubit coherence times. And there is no sidewall, as we can see here. The sidewall oxides can also act as loss mechanism in the qubit chips. So all these aspects are important. So here, after creating this trench in silicon, then we deposit the metal, and then we are not showing here. So after we deposit the metal, there will be hills and valleys, as Pops had mentioned before, and then we used chemical mechanical planarization. And here is the example why we need the chemical mechanical planarization to remove the extra metal, and only the metal will remain in this trench. So after the bottom electrode is established, then we deposit a sacrificial oxide, which is basically silicon dioxide. And using the 193 nanometer lithography and reactive ion etching, we create this trench. And then we deposit our tunnel barrier and the top electrode. Here is how the Josephson junction look like. So this is the bottom electrode, then tunnel barrier, and then the top electrode. Yeah, so we have ALD tantalum nitride in our tunnel barrier. So when we develop a new technology, first we need to establish different elements of it, and that is why that is what we did, and I will take you through different steps. So this is the fabrication flow, like the different steps that we have to take. But before starting the fabrication, what do we need to make sure? First, that whether we can get repeatable alpha tantalum phase across the entire wafer with good non-uniformity in terms of thickness, sheet resistance, and we can get alpha tantalum every time, whether I deposit it today or 1 year later. So alpha phase is important for quantum application because its TC is high and some other reasons. So using the SRD and the sheet resistance measurements, we confirmed that we are getting alpha tantalum every time. And the central image is the TM image of this tantalum nitride. So we need a tantalum nitride seed layer in order to form the alpha phase of tantalum. And we also confirmed that the sheet resistance non-uniformity is less than 5%. So we have good across wafer non-uniformity in terms of thickness, sheet resistance. We can get good alpha phase. So which means we have good thin film material for our bottom electrode and our top electrode. So now comes the next step, which is to establish the bottom electrode. So as I mentioned to you before, first we create the dielectric stack, silicon dioxide, silicon nitride, and then we create the trench. So the point of using this 300 millimeter fab is to get repeatable processes. And how do we make sure? Like Pop gave an example of the CMP process where they used eddy current sensor. So this is the reactive ion etching process. So first we create the pattern using the 193 nanometer lithography, and then we do etching. So we have to make sure that after the etching, it stops at silicon. So for that, in the fab, we use optical emission spectroscopy, where they detect the reflected light and they choose the wavelengths in such a way that when it reaches the silicon surface, we will know that it has reached the silicon surface and it will end the process. So here is an example of that. So we use different thicknesses of silicon dioxide, which is this. So for different thicknesses, we expect different endpoint time. So as you can see, the time is increasing as a function of thickness. So as a function of variation, like due to variations in the different consumables, different chamber Rye process, all those stuff, the process should remain the same. And that is that graph shows an example of that, where over a period of almost an year, the line width remains tightly distributed, and this is due to the endpoint scheme that is used in the fab. And after that is established, then we used an anisotropic etch, which exposes the 111 planes. And because this is a wet etch process, so there is no silicon damage created at the side pole, which is an important consideration for the quantum devices. So because this is due to the crystal nature itself. Yeah, we use a mask. So now we have established, we have created the trench, and this was just an example how the Rye process is repeatable over a period of 1 year. So that's the advantage of using the 300 millimeter fab. Next, we deposit the metal, which is the tantalum metal. So here you can see the hills and valleys. So we need to planarize the surface, and it should look like this. So we use the chemical mechanical planarization. So here is an example of how the CMP tool looks like from inside. So this is the platen. Here the wafer is on the backs. This is the wafer, and this is the slurry material. So the wafer, basically it's rotating and the platen is rotating in the anticlockwise direction. So it is removing the material, and there is a laser light that is being reflected from, that is incident on the wafer, and the reflected light is monitored. And by the change in the reflected light, it is determined that the metal is being removed. And that's how an endpoint algorithm is developed, that as a function of variations of the pad size, different things, different consumables, your CMP process gives you the same result every time. And here is an example where these 5 wafers were run at different times, but the resistance across a serpent structure on the wafer remains the same, as well as the leakage across a comb structure remains the same. So now we have established our bottom electrode. So there are some devices that, like I showed in the previous slides, that for a qubit device, we need 3 elements. what are the three elements? First is the junction, second is the capacitor, and third is readout resonator. So for some devices, we just need one. So for junction, we need bottom electrode, top electrode. So we need two levels, and we need to integrate those two levels and the tunnel barrier in between. But for some devices, such as the resonator, we need just one level. So this is an example of that. So after the bottom electrode, CMP is done. So the resonator fabrication is done. So this is an example of a inductively coupled resonator. And the right-hand side shows the microwave transmission results for this resonator. So we got good quality factor from this, and we are still working on it to improve our quality factors in partnership with national labs and SEEK. This data is taken at SEEK, and the bottom image shows the TM cross section of the side wall. So here you can see, so we need ALD tantalum nitride in order to grow the alpha tantalum phase, and there is no silicon damage here at the side wall. So which, as I mentioned before, is important for quantum chips. So these are the small details that we have to take into account when we are doing fabrication for quantum devices. Okay. So it serves two purposes. So one purpose is, in order to do the chemical mechanical planarization, the pattern density across the wafer should be uniform. And for that, like if there is just one metal here, okay, first let me describe the pattern. So this is a transmission line. Across this, a microwave signal is going, and then there is a coplanar waveguide resonator here, and we are measuring this transmission S21 as a function of frequency, and the dip is basically the resonance frequency. And then we have a resonator here. Then there is a ground plane, which is basically the metal around it, and this is silicon. So tantalum, silicon, tantalum. And we need these patterns, which are known as dummy fill, which are basically silicon, basically the holes. So these are the cheesing. Like in a butter, we do holes like cheesing, buttering. So these are required to have a uniform pattern density across the wafer, so that after the CMP, we get the same result everywhere. It's not like some portion is there is over polished and some portion is less polished. So that's what the purpose of this. And second purpose is, in qubit devices, you will usually see this. So in order to, so that there is no flux trapping and all the other effects. So it serves two purposes for us. Okay, so we have established our bottom electrode. In our junction fabrication, what is next? Tunnel barrier. So the tunnel barrier, when we develop a new technology, so we need to determine whether it satisfies the characteristics of a tunnel barrier or not. And what should be the characteristics of a tunnel barrier? Is that it should be insulating. And in order to determine its suitability for a tunnel barrier, we collaborated with Professor Zollner from New Mexico State University for spectroscopic ellipsometry measurements. And here is the graph showing the real and imaginary part of dielectric constant at different temperatures. And from the modeling, the band gap came out to be 2.1 eV, and there was no pre-carrier absorption. So this means from this, we determined that we can use it as a tunnel barrier, and its band gap is lower compared to the aluminum oxide, which is usually used as a tunnel barrier in aluminum-based junctions. So if it is lower, which means we can use thicker barriers for our Josephson junctions, which is another advantage, because when aluminum oxide is about like 1 nanometer or something, so it is very difficult to control the thickness and stuff. So here we have established that we can use ALD tantalum nitride as a tunnel barrier. So then what's the next step? The next step is to do the top electrode patterning and deposition and etching. So this is how the final device looks like. The left-hand side shows the SEM image of the junction. So this is a bridge junction. So this tantalum layer is forming a bridge. This is going to the 4-probe structure, this tantalum wire, and the junction is here basically. So this is the bottom electrode line. Then there is a barrier there which is not visible here, but it's visible as a hole here. And then this is the top electrode. And here is the TM cross section showing this the bottom tantalum, top tantalum insulating barrier. So now we have completed the Josephson junction fabrication. Next step is to determine how good our junction is. And for that, we do electrical test. So the left-hand side graph shows the cumulative distribution of resistances for junctions with different dimensions. So these are the square junctions, so 180 nanometer by 180 to 3 micron by 3 micron. So here we see that the resistances are changing as a function of the area, so which is as we expect. And next, here it shows how the resistance non-uniformity is varying as a function of junction dimensions, because we measured 26 sites distributed across the entire wafer. So the main point of doing this 300 millimeter fabrication is that we should get a tight distribution in terms of all the parameters of the junction, whether it is CD, critical dimensions, or it is the electrical properties, or it is the low temperature characteristics. So here we see that for lower dimension junctions, we have higher non-uniformity. We are working to improve that, but this is our, this shows that for lower dimensions, we have higher non-uniformity, but for the higher dimensions, we have good non-uniformity in terms of resistances. And this is the resistance area product, which is an important parameter for a Josephson junction. So it shows that this is flat after subtracting the effect of the lead wires, which is again good, and shows that we have good Josephson junction characteristics. So we have established that at room temperature, we have good Josephson junctions. Our next step is to go to low temperature, because for a superconductor, we have to go to the temperatures below superconducting transition temperature in order to determine its characteristics. So here we measure the current versus voltage curves for a junction with 4 nanometer ALD tantalum nitride in the barrier for different dimensions. So in this curve, when it is in superconducting state, the resistance is 0, and at the critical current, it switches to the normal state. And the voltage at which it switches, it's known as the characteristic voltage, which is about the same for all the dimensions of the junction. And so this goes through the linear curve goes through the 0. So this determines that this acts like a good junction, and the IC varies as a function of dimension. Here is the critical current density JC, IC divided by area, and it fits to the Siemens model. So from this, we determined that, yes, it is fitting to the Josephson junction criteria, and these are the characteristic parameters of these Josephson junctions. Okay, so now we have determined the Josephson junction characteristics. Next, we tested the aging of junctions, because in the traditional aluminum oxide based junctions, Aging is an important parameter because the aluminum oxide degrades with time. So here we tested the junctions at an interval of 140 days. It shows the same IV characteristics, which means it is stable over time, it is not degrading, and which is due to the ALD tantalum nitride is thermally stable. So which is another advantage of using this technology. So up to now, we have done resonators, which was on the bottom electrode only. And we have done Josephson junction. What was the third element? Capacitor. So
did you literally pull the whole 300 millimeter wafer, or was it cut up first?
we diced it
Okay.
at the TAP facility in Rochester. We send the wafers there, they dice it, and we get small chiplets like 5 millimeter by 5 millimeter. And then we measured this at Air Force Research Lab, ROM, in their adiabatic diamagnetic refrigerator.
So that's another area of research that clearly is going to be important to you guys' engagement. How do you package these research to extract the communication? The other point to note is there are vendors, imports, that is making a 300 millimeter variable that have 2 meter variable. So maybe we'll get it, but that won't allow us to measure the really heavy temperatures in order to see performance, but it allows us to test at 300 millimeter scale to know whether or not our junctions are working, they can go down to 1.7 Kelvin.
Thank you, Pops. Yeah, so packaging is another area where you can think of making your career. Like you can see that cross point, it is for the thinner ALD tantalum nitride because the critical currents were higher. It was having self-heating effect. So we need proper thermalization, like having proper contact with copper, having a better package design in order to reduce all these effects. So we are working on those things. So that is also something to keep in mind. Okay, so now comes the third element, which is capacitor. So here, again, the advantage of working at this 300 millimeter scale and using this state-of-the-art tools is we can get several devices at the same time, but the devices of different types. So here you can see we are using Damascene capacitor. Damascene means creating the trench in silicon. And we are using silicon as dielectric, which is crystalline. So crystalline capacitors made with crystalline silicon, the dielectric between the two tantalum is expected to give us good quality factors. So which means we should get good coherence times when we use it in qubit device. So we create the trench in silicon and then we deposit the tantalum metal. So for the narrow CD, there is a pinch off here. And for the wider CD, when we deposit copper on top, the copper will be deposited there. So there is vacuum here basically. So this acts like a tantalum capacitor, and that can act like a quasi-particle trap because quasi-particle poisoning is one of the issues for qubit devices. So they can trap the quasi-particles. So we can use both of these on the same chip depending on the design. And one can act like Damascene capacitor, silicon-based Damascene capacitor with improved quality factors. Other can be used to trap the quasi-particles and improve the quality, improve the qubit coherence times. So So, like for quantum devices, it can be affected by external environment. So in the external environment, we have several things like magnetic fields or the cosmic rays. So from the cosmic rays, the cosmic radiation, so these quasi-particles are basically the excitations of the Cooper pair. They excite the Cooper pair and make them into single particle states, which are the quasi-particle, which creates the dissipation and affect the qubit coherence times. But using a normal metal, it can be trapped into these particular areas and not affect the qubit, which is somewhere else on the chip. Yeah.
So I remember correctly that someone was going to put a divergent refrigerator down some mine shaft somewhere that actually test this, and if I'm remembering that correctly, was that done, and if so, does it really actually support that it's cosmic rays versus something else? I'm just curious.
So we are working with PNNL people who have these underground facilities, and we are working with them for resonators, but we haven't tested this. So
Right. No, but I guess, right, so there is of course evidence that of course when you deliberately, add a source of radiation, it gets worse. But that makes physical sense, and that's a different statement than is it sort of straight cosmic rays, and if it is straight cosmic rays, then I guess traps like this could help, and then also you can do some other kind of shield.
So we are working on tantalum-based Damascene capacitor as well as the aluminum-based capacitor. So here is a picture of the aluminum-based Damascene capacitor. Yeah, and another advantage of using this is, like, as you might have remembered, I showed this qubit chip, IBM 5-qubit processor. So this is a question for you. Which element of the qubit is taking the biggest part in this chip? So first of all, qubit has 3 parts. One is capacitor and readout resonator. Which one is taking the maximum part? Yeah, because good. So we have the CPW resonate, the big resonators. But if we replace this resonator with a resonator which is a lumped element resonator made of this capacitor and a nanowire which acts like a kinetic inductance and provides the inductance for that resonator. Lumped means it has L and C component, inductive and capacitive. So then the qubit footprint will become very small. So the size of the qubit will become very small. So that is another advantage of using this capacitor and the lumped element resonator based on this capacitor.
Sorry. So these are usually operated somewhere.
Yes, around 5 gigahertz. So there are 2 things. One is coupling, other is frequency. So frequency should be in the range of 5 gigahertz, and the coupling should be such that it should be able to read the qubit state. So by using this LC and this lumped element resonator, we can tune the frequency by having the different dimensions of capacitor and the nanowire inductor. But for coupling, I think that is again an area of research. How much will be the coupling? And yeah, that is again.
And my thinking is that if you open a window, it is a traveling wave or a standing wave that literally have got the frequency
Right.
when we down to So whereas in non-relevant resonance, the energy of that microwave is stored in the diameter of the duct. And so there is not the same spatial sort of you need to fit standing wave between yeah, I find it sort of practical to do that, but clearly an OER that is 1/10 the size of the wavelength can still or maybe the other way to think about it is if let us say you have a coax waveguide. So the coax waveguide transmits the wave in the field in between, right? And so depending on the engineering of that coax waveguide,
I'm just curious. Go ahead. Thank you.
And so we have talked about resonators, capacitors. For lumped element resonators, we need capacitor and then we need inductor. And we plan to use nanowire as a kinetic inductor, as the source of that inductor. So for that, we fabricated again Damascene nanowires. As you can see here, this is a tantalum nitride Damascene nanowire. And the advantage of using this scheme is that we can fill it with anything. But here, like either dielectric or any other material, we choose copper here, which acts like a heat sink. So like Pops mentioned about the superconducting nanowire single photon detector, how it detects a single photon. Like in superconducting nanowire, below the superconducting transition temperature, we have Cooper pairs. Like above the superconducting transition, we have electrons in metals. So when it absorbs a photon, the Cooper pair breaks. And when it breaks, that's how means the electronics is like that. It detects that it has absorbed a photon. But there is some heat dissipation that has happened at that time. So if we have this copper on top, which can absorb the heat, so then it will improve the reset times of those single superconducting nanowire single photon detectors. So that is the advantage of using copper. We characterize the IV curves for these nanowires, and you can see in this graph for two different nanowire widths how the IV curves look like, the IC scales as a function of the width of nanowire for two different thicknesses of tantalum nitride. And this graph is for the niobium nitride nanowire and also for the blanket films for different nitrogen flow, we can vary the transition temperature as you can see here. So here also we can see the synergy between the fields using the same materials. Like Pops showed one graph where we had the same material, but we could go to different fields. So the same nanowire can be used for single photon detectors, which is used in photonics quantum computing, and it can be used as a kinetic inductor in the lumped element resonator in superconducting quantum computing. So that's how the synergy works. And so here is basically all the devices that I have described so far. That was the quasi-particle trap capacitor on top of which I have this kinetic inductance element. So this is a lumped element resonator. Then we have this coplanar waveguide, where we just established the bottom electrode with the ground plane around it. This is a Josephson junction. So using the 300 millimeter fabrication, we can fabricate all these devices at the same time in the same mask by using different litho levels, which Pops described the 8 litho levels that we plan to have in our new reticle. And you are welcome to include your design if you want to work with us. Yeah. So in the earlier design, like in the earlier slides, I just showed we had this where I showed the resonator. We had the CPW and the ground plane. There was no bridge like this. So in this new reticle, we plan to have this air bridge. Basically, this is a bridge of the using the top electrode, and there is no so this can tie the ground planes. Like in a normal qubit chip, you might, I haven't shown that diagram. Usually across the transmission line, they put wire bonds everywhere across the transmission line from this end of ground plane to other ground plane, because they want to have same potential difference everywhere. But those wire bonds, when we create the wire bond, they create damage on the chip. So here, basically, we have fabricated it. We don't need a wire bond. So it will reduce the damage. So it is again an example how every small thing matters on a quantum chip. Yeah. Yeah, shielding. The tantalum film, polycrystalline. Okay, so next I will hand over to Pops.
You want to turn off your thing? Okay, we're back. Thank you again, Ekta. That was great. Well done. I promise I won't ask you questions like she did. She's a very tough taskmaster. But okay, so now we're nearing the end of your summer school, and one of the things that Satya said is, why don't we share with you our feelings about collaboration? And I saw earlier in the first day you were giving a talk about collaboration. So I want to say this is a biased viewpoint. This is my viewpoint, and if there is any disagreement between what I say and what he says, he's right, I'm wrong, right? So. So the one thing I want to say is, your life is going to be defined by collaboration, right? I mean, humanity is about collaboration. We're going to get to Mars by collaboration. And so the one mind frame that I would like to suggest that you take away when you approach collaborations is, don't think about, I'm going to lead this collaboration, right? Because that mind frame will come across your behavior. It will infect the collaboration in perhaps not so positive way. You guys are all leaders. So the very fact that you are here in a premier summer school means that you will be leading, right? But when you approach the collaboration, think of it as, what is the leadership, like Lincoln said, of the collaboration? Where can this collaboration lead? And it is by the collaboration that, the work done by the collaboration that will get you to lead. And of course, off the collaboration. The analogy is not very, very precise. But the point is, think of the collaboration that you happen to be showing the way, perhaps, but the collaboration is the entity that is doing the leading, not so much about how. And then the other thing is, there is always going to be questions, okay, can we collaborate? How do we do that? You need to keep in mind, and we will give you some examples, that a collaboration succeeds when there is a common understanding of the need, right? Where you don't need to convince we won't even form if the other people don't think a collaboration is necessary, because there is a clear and present danger that can be solved by the two of you getting together. And it is useful to make sure that there is a clear understanding of relative strengths, right? I mean, what can you do? Like I said, none of us are capable of handling everything that needs to be done. So it is useful to make sure that you understand. So I want to give you some examples of history. I used to have a lot more hair. So from all that time, I want to share with you what we've done. So Semitech, and I had the good fortune of being involved with Semitech to some extent when I was at TI, and also when Semitech moved to Austin. And some of you might know it was started in the 1980s. There was a special act of Congress that basically said the semiconductor industry, you will be allowed to participate in collaborative research, and we will not go after you for antitrust or whatnot. And that was because of that, and which is why it was the question, panic-based, because there was that perception at that time that the Japanese semiconductor industry would come and take over all of the US industry, right? And so everybody got together and said, okay, what can we do to make sure that we can meet this challenge? And Semitech was formed. And largely, I believe it was very successful. What are the reasons why it was successful then? There was, of course, this need that everybody perceived, rightly or wrongly, right? I mean, you could say the Japanese threat dwindled, but clearly Semitech succeeded in many of the things that it was doing. Some of the examples were, defect reduction roadmaps, right? I mean, where people got together and established a roadmap. And to this day, people say, okay, let's establish a roadmap. And I feel the roadmap serves a purpose when it satisfies a need. You don't need to create a roadmap just because there is some technology. Why did the roadmap work at that time? Because there was a large number of entities, a huge community, many companies serving a range of device manufacturers, right? And in contrast to now, actually, there's a colleague of mine, he's now at IBM, who made the point, you can count all the major levels of the semiconductor industry by fingers of one hand. The people that drive the technology, the Google, the NVIDIA, whatnot, and then the people that make it, TSMC, Intel, Samsung, they're all, you will never get past 5. The number of equipment makers, Applied Materials, Tokyo Electron, ASML, KLA-Tencor, the industry has consolidated over since the 1980s now, right? But maybe things will change, right? I mean, clearly things are febrile right now. But at that time, it was necessary to create a roadmap so that these 40, 50, there was a poster that describes Semitech partnerships. It's like, logos that were too small to see, right? And so it needed the unifying principle of a roadmap in order to pull everybody together. And it worked great. The other thing, of course, is one of the first founders or the first CEOs of Semitech was Bob Noyce, from one of the inventors of the transistor, right? Of the IC rather. He insisted that every company need to send its top people there. He didn't want it to be a place where people got sent off if they didn't succeed in the mothership, right? So it was full of really smart, inventive people, and they continued to address the problem. And what I mean to say, an evolving mission is that after the 200 millimeter wafer size was done, as the industry moved to 300 millimeter, Semitech did a great job through the i300i consortium in order to allow, because the amount of investment that was required from the vendor companies, the CMP tool makers and everybody, was ungodly. And they couldn't see the value till after the entire industry had moved, right? And so, in fact, recently, NY Creates was involved with the 450 millimeter consortium, the G450C. And so, yes, they were able to show that you can go to 450, but the industry didn't need it, and so that effort closed down as a result of a successful demonstration that yes, it is possible. But even okay, I mean, maybe I should turn off the recording, but My personal perspective is that industry consolidation got to the point where the extra, billions of dollars that would be needed, the main players probably felt, do we need it right now? It was a business decision, maybe is the correct way to say it.
Ships have bigger, smaller.
Right.
So
Right. No, I mean, but in terms of I would argue, I mean, your point is well taken, but I would argue the chip size, as the chips get smaller, yield definitely goes up, no matter what node you're on, wherever, right?
the exposure, right? The exposure per small.
Right, 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 right. I know
I just, it feels right.
that you don't need to go there. Yeah, yeah. I mean, I've been thinking, habituated to think in terms of the R squared, right? I mean, the number of chips that are at the wafer edge are so much more than what you have in the wafer center. And so there are some companies that say, we don't care about the wafer center, get the edge to yield, because that's where most chips are located. But I think mainly business reasons to say, consolidation, cost. And I think your point about small chips and heterogeneous integration plays perhaps a bigger role, because right now, and which goes back to the whole packaging idea, there's a big heterogeneous integration center at NY Creates, led by IBM, where you don't want to put all the functionality on the same chip. Maybe the similarity is with the large language models versus small language models. If you've got a large language model, you've got to invest billions of dollars in order to do it, lots of kilowatt hours. But if you're able to string together a lot of small language models, which is what people I believe are trying, I'm not an AI guy, but I believe that is one way in which the technology can continue without demanding more power than there is on the earth. Similarly, rather than saying this one chip that you print on a wafer has to do all functionality, you might say, let's make this do this, at say 2 nanometer node, get a 130 nanometer node chip to do whatever else, get a silicon carbide chip to do something else, get power management from somewhere else, and so you build them together as a package. So that might be it. But the point I wanted to make here is, when you are part of a consortium, you start off with a clear need, but you have to also recognize that there are times when that need will change, and the consortium or the collaboration has got to change with it, otherwise you'll wither and die. I mean, a great example of a long-standing entity, maybe it's not a collaboration, but is the Cornell Nanofab, right? I mean, they've been there for a long time, and they are still going strong, right? And it's because they are continuing to innovate in order to answer the need that's present. Switching from Sematech to NY Creates, this is something that we're justifiably proud of, right? It's a place where literally competitors collaborate. Applied Materials and Tokyo Electron, you cannot leave them alone on the street. They'll kill each other, right? So, but they are fierce competitors in the marketplace, but they are able to collaborate at NY Creates. Why? It is because we have found a solution to a major hindrance. At NY Creates, we have a manufacturing execution system and all the intellectual property controls that allows you, let's say, from Applied Materials to say, I need EUV lithography. Okay, and so there is the framework, and NY Creates engineers that are there to provide a black box solution to you. Or you are Tokyo Electron and you want to get CMP from Applied Materials, right? Everybody needs everybody else. And this is a way in which we have made it possible for people to collaborate without needing to know the crown jewels of the other industry partner. Now, I mean, it doesn't always work. And what I mean by counter is there is a big need in the industry right now. You have heard of the digital twin effort and so on, to do PMs, which is not preventive maintenance, but predictive maintenance. We waste a lot of money saying, okay, it's time, change the pad. It's time, change this. Whether or not that pad is good or bad doesn't matter, because the risk of making a mistake is so high. But if you can harvest all that data and use it in order to predict that this is, if you don't do it now, one more day and you're dead, or you're likely to be dead, there is going to be a lot of sustainability savings, cost savings, everything, right? And so this is useful, but it means that companies have got to be willing to say, these are the secrets of how my tool is degrading, and that is difficult to do. So that's a challenge that is being tackled right now. So when you are thinking of collaboration, if you're able to say what are the major hindrances, and if you're able to say this collaboration will address that, then you're bound for success. So the other thing is, so various examples to illustrate how you could collaborate with different people. So Envi Creates, for instance, engages with startups. So Tetramem is a memory company. Menlo Micro makes switches of some kind, not of some kind, MEMS switches. And then Ekta and I work with Seek on superconducting devices. And then there are partners at Envi Creates that are working with PsiQuantum on integrated photonic quantum computing devices. The way in which we work with these startups is yet again different. So the point I want to make here is you want to be able to meet people where they are, right? A startup that is like PsiQuantum, it's got huge funding. What they want is going to be different. In fact, they run their own wafers and they keep tight control of what they are doing. Whereas, Menlo Micro is still not running wafers in the line through and through, but they are able to say, oh, how can we introduce glass wafers, et cetera, et cetera. So you need to be able to find solutions for each member of your collaboration so that, you can make sure that it works together. And then, of course, there are, how do you collaborate with large industry groups? Here is, our collaboration with Fraunhofer, IPMS. We were talking to them about maybe we can give them, they're looking at hafnium nitride and zirconium nitride resonators. So we are saying, how can we work together? Maybe we can generate some wafers that they can use. We can do lithography for them, et cetera. They don't have lithography at 300 millimeter scale. C2MI is a packaging entity based in across the border in Canada. So clearly there are, it's a marriage made in heaven. And then here is SEMI's leader of sustainability talking to our president on how we can work together to enhance sustainability. Clearly, I'm sure you guys heard PFAS is a major problem for the semiconductor industry. The photoresist that we are so fond of are all, they have PFAS in them. And so there isn't a solution that is known right now. So if the government immediately were to say, we have to ban PFAS in the next 3 years. Yes. Yes. Frantic is the word. Yes. Right. So, but that is also an opportunity, right, to try and, metal organic resist may be less PFAS containing. It is the chemical amplification of the photoresist that has the PFAS moiety in it. So, it'll be good if you're able to say, participate in that effort. And clearly, you need chemists, you need electrical engineers, you need everybody. So these are opportunities for collaboration. And over to you.
So, hi again. So Pops has already talked about the bigger level collaboration stuff. What I will talk about is like how we can do collaboration at different levels, whether we are a student or we are a professional. So when we work together, alone we can do only so little, but together we can do so much. So this picture is just an example of how we can help each other and grow together. So you might already be doing all that stuff, but I'm just sharing my experience. Like when I was in PhD, so I had few things in my lab, but so many things not in my lab. So, but the other researchers, they had those things in their lab. They were in different institutes. I didn't even know them. So I just searched for it. I emailed them. So I went there. It was far off place, but I went there. So I explained my project to them. They learned from my project. I learned from their techniques, like it was like magnetic domain imaging, how to look at domains and structure. So I made the pattern structure. So they also learned like they can imagine image domains in those different kinds of pattern structures. So that collaboration basically was fruitful for both of us. So that is like a small level of collaboration example. And then, and collaboration can be of any type. It can be national. So that was a national level collaboration. It was like in my own country, and then international collaboration. Like during my PhD, I went to University of Cambridge for 6 months. So I met with my professor there at a conference, which was Applied Superconductivity Conference. So I gave my talk and he was there, and I just met with him for 5 minutes, I remember. It's after my talk because he had to leave after that. So he said, yeah, it is possible. We can do something. So I explained what I want to do, but I didn't stop there. So I kept following up after that. And it took me, the conference was in September 2017, I think, and I went there in June 2018. So it took such a long time. So because I kept following with him, and then how to get the fellowship and stuff, all those stuff. And I went there, like I had a great experience there because of the people who were there. I learned something from everyone, like from one person, I learned how to use their cryogenic equipment. From one person, I learned how to use the focused ion beam to make a Josephson junction. From another person, I learned how to do the analysis. And what I gave is my effort. So it was a collaboration which helped me to grow and for them to have, means what I gave to them is the idea, means the new things that we could work on. And that's how that collaboration spirit basically, means till now I'm in connection with them, and these are like lifelong collaborations. It did not end up there. So, but we have to be consistent. First, we have to have the courage to ask, and then we have to be consistent, and we have to keep this collaboration. Like with Satya, I think we met with Satya in 2022. And now he invited us for this talk. We discussed at APS March meeting some different new concepts that maybe we can do, we can try, and all those stuff. So this is again an example of a collaboration, or you people are here, you must be talking to each other, oh, we can do this, we can do that. So that is like student level collaboration. And then I will say about quantum. So quantum is an interdisciplinary field. You could be a material scientist, you could be an electrical engineering, you could be doing physics or computer science or chemistry. You can go to quantum through any of these fields, because as Pops mentioned, as I showed in my talk, the different elements, we need different processes, we need fabrication, we need materials, we need etch experts, we need lithography experts, we need designer, we need data scientist, everything. So the quantum, and we need the collaboration. You could be working at any place, whether you are in a startup, or you are in a national lab, or industry, academia, non-profit. The success in quantum is possible only by synergy between all these different entities. And you can go to quantum through any research, through any major. And my work at NY Creates is a great example of that. So I'm working with national lab, like Brookhaven National Lab. Maybe I will. So these are our partners, basically. So I'm working with national labs, whether it is Brookhaven National Lab, or it is, I forgot to add PNNL. No, yeah, it's there. So Pacific Northwest National Lab. So we are working for our resonator measurements, where they have underground facility for this cosmic ray absorption. There's no cosmic ray. So we are working together. So we are fabricating at our site, and at their site they are doing measurement, and then we meet and we get some fruitful results. We are working with Brookhaven National Lab. They are also for different projects, and sometimes you have to, the other person has the equipment, but they don't have the expertise. They don't know about your project itself. So you have to explain to them how to use that equipment for your particular purpose. So it should be, it's a two-way street. It's not like just one way. And we are also working with different academic entities. For example, New Mexico State University. I showed the spectroscopic ellipsometry results. So I met with them in 2022 in AVS American Vacuum Society conference. So I attended their students' talk, and I found that they are doing that. Okay, we need that. So I approached him. He was just sitting there, and he said, yes, you can send me your samples. We sent them, and they presented those results in the next year conference, AVS. So that's how the collaboration works. So it was good for them, it was good for us. And similarly, so C2QA is Co-Design Center for Quantum Advantage. So which is basically a collaboration of these different entities. It brings together the academic entities like Yale University, National Lab, Brookhaven National Lab, and like us, NY Creates. Professor Kushwaha is also part of that. So this is a great example of how different aspects can be improved by collaboration. And this also allows us to work with different entities, because you need to justify, you need to have that project in order to invest time and invest your time, because without money, nothing works. So, and with Seek, like we are working with them for the cryogenic control for the measurements, television refrigerator. We do fabrication at our site, like Pope's given example, and they do cryo control, SFQ, single flux quantum control of superconducting qubits. Air Force Research Lab. So we measured our Josephson junctions in their refrigerator, and Tokyo Electron is on our site. So we work with them on different equipments, fabrication and stuff. So, but in each collaboration, what matters is they are also leading something, we are also leading something. There is no one is up, other is down, or something like that. Everybody is equal, and we should lead our part, and we should allow the other person to lead their part. And that's how we progress together, I think.
Okay, let's thank.
Thank you.
So, when you work with the fluid materials and when you try to maybe design some chips from fluid materials, so I'm just curious, like if you try to make them in a compact chip, is there any problem with the electrostatic fluctuations? Because those fluctuations